In the next short set of videos, we're going to be looking at ordinary differential equations. So most of the fundamental laws of physics, mechanics, electromagnetism, chemical reactions, and a whole bunch of other things that as engineers we need to worry about, they're framed in terms of spatial and temporal changes of different variables. So for example, dx dt is equal to velocity. dv dt is equal to force divided by mass, or equivalently acceleration. d squared x dt squared is equal to minus kx. This is the equation that describes simple harmonic motion. d by dt of temperature is equal to kappa times d squared t by dx squared. This is the conduction or heat equation. dq dt equals minus u times dq dx. This is the advection equation that describes how a quantity q is advected by a velocity field u. These equations usually describe how one variable changes in time and or in space as a function of time, space, and the other system variables. In all of these equations, we can see that derivatives appear on one or perhaps both sides of the equation. And for this reason, these are called differential equations, because we have derivatives on one or both sides. So let's introduce a little bit of terminology. Let's go back to our example of the falling bungee jumper, where we saw previously that dv dt was equal to g minus cd on m times v squared. So if that's the differential equation that we have, we call the dependent variable the variable that is being differentiated, v. For a single equation, there is only one dependent variable. And it's called the dependent variable because it depends on the other variable. So the velocity here depends on time. Therefore, we call the independent variable the variable, or perhaps variables, that are being differentiated with respect to. And in the equation up here, the independent variable is t, or time. An ordinary differential equation is a differential equation that has only one independent variable. So the equation here is an ordinary differential equation because there's only one independent variable. A partial differential equation, or a PDE, is a differential equation that has multiple independent variables. So for example, the heat equation that we saw previously, dt by dt is equal to kappa times d squared t by dx squared, is a partial differential equation because one side of the equation depends on a derivative with respect to time, the other side depends on a derivative with respect to space, or x. So if we start off with a physical law, for example, F is equal to ma, we saw that in the case of the bungee jumper, we can derive an ordinary differential equation. In that particular case, that was the ordinary differential equation that we derived. Ideally, in the real world, we'd be able to take that ordinary differential equation and come up with an analytic solution. That's really what we'd like to be able to do. It turns out, as you might expect, that in many, many cases of practical interest, there is no analytic solution. Therefore, we need to devise some kind of numerical technique for solving these equations. And that's what this particular section of Eng 1060 is all about. It's deriving numerical methods to solve ordinary differential equations. So in this unit, we're only going to consider first order ODEs. And when I say first order in this sense, it means that the highest derivative is the first derivative. We're not going to worry about anything where there's second derivatives or third or fourth order derivatives. And what we're going to do is we will write the generic first order equation as dy dt is equal to some function of t and y. So we can write any first order ODE like this. Let's be really clear as to what this equation here actually represents. So y is the solution of the equation. And we know that y varies in time because dy dt is not equal to 0. So y is a function of time. But it's the solution that we're looking for. dy dt is the first derivative of the solution, i.e. it's the slope of the solution with respect to time. That's what the left-hand side of this equation is. And f of y and t is just some function. We saw that previously it was equal to g minus cdm times v squared for our bungee jumper equation. And it will be different, of course, for different equations. This equation is equivalent to saying the slope of the solution is some function of the solution and time. So you can see that the solution appears on both sides of this equation, both the left and the right-hand sides. On the left-hand side here, it occurs in a derivative, and on the right-hand side, it occurs in some function. So you can see it's not necessarily a straightforward problem to solve. Let's have a look at a specific example. So dy dt is equal to yt minus y cubed. If we imagine that our black line there is a solution to this equation, and in actual fact it is, what this equation is saying is that at any value of t, and let's take the example that t is equal to 4, we're going to have a solution. And the solution is y, and in this particular example, y is equal to 1.72. We only know this, of course, because we've actually solved the equation. And at this point t, y, the slope of the function dy dt is given by the right-hand side. That's yt minus y cubed. So in this case, the solution would be 1.72 times 4 minus 1.72 all cubed. And that would be the slope of the solution at that red dot in the figure. One question that's actually a very important question to ask is this black solution here, this black line solution, is this the only solution we have to this ordinary differential equation? The answer is most definitively no. In order to uniquely specify the solution to this first order equation here, we must specify what is called an initial condition. And an initial condition is that the solution y is equal to some value when t is equal to some other specified value. So for example, that black line curve there is the solution to this differential equation when y is equal to 0.001 at time is equal to 0. That's that particular solution. Other initial conditions will give different solutions. So for example, if y is equal to negative 0.001 at t is equal to 0, we get the dashed black line. If we choose a value of y is equal to 10 to the minus 4 at time is equal to 0, we get the blue line there. Negative 10 to the minus 4, we get the blue dashed line. And 10 to the minus 1, and various other values. So depending on the initial condition, we will get different solutions to the ordinary differential equation. So this problem, these first order ODEs, are often called initial value problems because you need to specify an initial value to get started. Now, we specified the initial value here at time is equal to 0. We don't have to specify at time is equal to 0. For example, we could specify the initial condition at time is equal to 2, and if we said it was equal to 0.5, we'd still get this pink solution here, or magenta solution here. So that's all I wanted to do by way of talking about an introduction to ordinary differential equations. Now let's go and have a bit of a look at how we might be able to solve them.